Can it happen that whatever be the starting state, I will always end up in the same state in the long run? The mu n kind of tends to some fixed state, W, as n tends to infinity. Can it happen for all Markov chains? It's easy to see that there are these trivial cases when this cut cannot happen. Why do we need some mystery? That is because we can have Markov chains having two set of vertices which are not even connected. So something like this, if this is the Markov chain, there's a single Markov chain, then what happens is that if I start on the left side, then I will stay on the left side. If I start on the right side, then I will stay on the right side. So this kind of Markov chain will not converge to the same distribution. There is another case. Let's say this Markov chain, which we have already seen. So again, if I look at even time steps, I will be on right side. If I look at odd steps, I will be on the left side. In these cases, we cannot converge to a, barring these exceptions, we can define something which is called a regular Markov chain. What is a Markov chain? It will remove these trivial possibilities. It will put just a simple constraint in some sense that every vertex is, there is a probability of going from every state to every state, and there is some probability of staying at your own state also. So taking care of both of these things, we will define regular Markov chain as something such that there exists an M for which, if I look at the ijth entry of M to the capital M, it is greater than 0 for all I comma j in my states. It is important to remember the order of quantifiers here. It is saying that there exists a single M. It could be very big, I don't care, but there is a single M. When I look at that single M, every entry of M to the M to the small m, is non-zero and positive. If I start with positive entries, then over it will remain positive. So important thing is that every entry is non-zero. Just with the simple restriction, which is true for almost all natural Markov chains, you will see that we will be able to prove that it converges to a fixed distribution. We will define it more formally later, but this fixed distribution will be called a stationary distribution. So you start with any state of your liking, but if you run the Markov chain long enough, it will converge to a fixed distribution. This only happens for regular Markov. It should surprise you. To prove this goal, we will start with a Markov chain M, which is regular. So that means we have small m such that this quantity is greater than 0 for all I comma j. What we want to prove is that there exists a vector W such that W is W transpose. So if I am in state W, then the next step also I will stay in state W. This is how I formally define a stationary distribution. It is one eigenvector for M transpose. Remember the definition of eigenvectors and eigenvalues? W is a eigenvector of M transpose with eigenvalue 1. That is what we call a stationary distribution. And we will also show that irrespective of mu 0, in a long run, mu 0 Mn will tend to W. It does not depend on mu 0. Remember that we initially gave the intuition that stationary distribution is the fixed distribution where we move to. And here we are defining stationary distribution as one eigenvector. But by the end of the proof, you will see that both the definitions have actually coincided. The one eigenvector, that is one definition. What distribution we converge to, that's another definition. But both of them are going to be same in the case of Markov chain. And that's why we are calling both of them as the stationary distribution. The formal definition of stationary distribution is this. So how do we prove that we tend to the stationary distribution? Not surprisingly, we have to look at the behavior of m to the n. Actually, it is better to look at the behavior of q to the n, where I define q as m steps of the initial Markov chain, because now I know that every entry of qij is positive. The long time behavior of m and q should be similar. If I just multiply by a constant, so q to the n is m to the nm, and since n is tending to infinity, both these behaviors will look the same. So I'm going to look at q to the power n. This is the most important theorem, which will show that q and y is going to be a constant. There's a difference between a constant vector and a fixed vector. Constant vector means that this is going to be a vector whose every entry is same, though the entry can depend on the vector y. Okay, so this is a constant vector. Every entry is the same. It is not fixed vector. But this is surprising that everything goes to a constant vector. But this is not an abelition of a Markov chain because I'm multiplying on the right. In the case of Markov chain, I multiply it on the left. So this is not the abelition of Markov chain. I'm just looking at the behavior of q to the power n. And this actually should not be surprising. What do I do? You can prove that every row of q is a probability vector. That means all entries are non-zero and sum to 1. If this is true, when I multiply by q to the q times y, I'm basically averaging out entries of y. So y itself was a probability vector. When I average it entries, all the entries come closer and closer. Let's say the maximum entry was m0 and minimum entry was m0. Now if I look at qty, the maximum entry will be mt and small mt. What I want to show is that this is much smaller than m0 minus m0 as t tends to infinity. So again, the intuition is that q averages out the entries. I will not go into detail. At this point, you should prove it as an exercise. If not, you can just take a look at the notes. It's a 4-line proof with the same intuition that since the entries of q are a probability vector, they average out the entries of y. So in every step, these quantities, so you will be able to prove that m1 minus m1 is less than some constant times m0 minus m0. This is less than 1. And you keep doing this and you see that it will become smaller and smaller. So my advice is you try to prove it formally. If you can't, take a look at the proof in the notes. This is good enough. We have proved that mn minus mn is going to be c to the n m0 minus m0, where c is less than 1. This is showing that as n tends to infinity, the maximum entry and minimum entry are tending to 0, which is same as saying that q and y tends to a constant vector. If the maximum entry and the minimum entry are the same, that means all the entries are same. So this proves a theorem. And this almost proves what we need. I'm going to give an informal argument, ignoring the limits, to prove that the regular Markov chain converges to the fixed vector using this theorem we have just proved. Remember that q and y is equal to cy. This is the all ones vector, boldface 1, for all y where y is a probability vector. This was the content of this theorem. And remember, Cy can depend on y. Once I know this, going back to m, nm will be making things unnecessarily complicated. So I will just replace them by n again. It's a variable. So let's assume this, that there is an n, there's a big enough n so that mny is equal to cy1. It's a constant. And this actually tells us a lot. You just fix y as basis vectors. That means, remember ei, it's just 0, 1 at the ith place. So if you place y as the basis vector, then mn ei gives you the ith column of mn. So this is saying that my ith column is a constant vector. If I want to look at mn, all the columns are constants. So this is C1, C2, C. All columns are constant. They might be different constant vectors, but this implies all rows are fixed vectors. You see that all rows are same. C1, C2, Ci, C1, C2, Ci, C1, C2, Ci. So all rows are same. Call this vector W. What we were able to prove is all rows of m to the n look like a fixed vector W. And not surprisingly, this W is going to be our stationary. If y is a probability vector, then m and y, you can easily show that if all the rows are W, then y transpose mn is going to be W. Whatever be my starting vector, if you want to know it by mu, then mu transpose m to the n is going to be W. Because every row is a fixed vector W, mu is a property. So this shows we always converge to W. The only thing remaining to prove is that we have W as the stationary distribution. That means formally it's a one eigenvector. M to the n plus 1 also will satisfy the same thing. All rows of m to the n plus 1 are W. This is not hard to show. You can take it as an exercise. So now W is equal to W transpose mn plus 1 is equal to W transpose m to the n, m is equal to W transpose m. So this shows that W is a one eigenvector for m transpose. It's a stationary. This completes our goal. We are able to prove two things. The W is the stationary distribution. That means there exists a distribution such that W transpose is equal to W transpose M, the existence. And second thing is, irrespective of mu, mu transpose M to the N tends to W as M tends to. A regular Markov chain has a very nice behavior. In the long run, all of them converge to a state. And thing which is important is that there exists a stationary distribution. This ends our lecture. We will see in the next lecture how to use it in computer science. Thank you.